This will be an introduction to bonding. We're doing this ahead of you learning how to name compounds and write formulas because there are different ways to name compounds based on the type of bonding that is occurring. So we want to have a little introduction so you kind of understand the difference. The reason that we look at bonding is that the properties of a substance in some ways depend on the bonding between the atoms. That's what we're going to look at in this discussion. The shape of the molecules and the interactions between the molecules will also affect the properties, but we're going to talk about those later. So here's an example. We have one of the allotropes of carbon is graphite. And you see from this picture that in graphite we have strong carbon-to-carbon bonds in 2 dimensions, but then the 3rd dimension we have relatively weak bonding. So in graphite, the carbon atoms sort of are bonded in like sheets that are then sort of attracted to each other, but not strongly bonded to each other. Whereas in diamond, another allotrope of carbon, we have strong bonds, carbon-to-carbon bonds, in all 3 dimensions. So very rigid structure. And these differences can affect their properties. And so in this slide you can see kind of some examples. Both substances are pure carbon, it's just that the bonding is different, and so that affects the properties. Another allotrope of carbon are Buckminster fullerenes, or Buckyballs as they're called. And again, different types of bonding, different properties. Okay, so let's talk a little bit about the basics of chemical bonds. Chemical bonds are formed because, as we've talked about before, the atoms want that nice, stable, noble gas configuration. They want full S and P sublevels in their outermost shell. Okay, and so the other thing to think about is that these bonds are the result of electrostatic forces, something positive attracted to something negative. So in all the cases of discussing the bonds, if I ask you to tell me the difference between one type of bond and another, really think about it and go back to what is the positive thing that's attracted to what negative thing. Okay, keep that kind of in your mind as we go through this discussion. There are 3 bond types we're going to discuss. Metallic, which is a metal bonded to a metal. Ionic, which is metal bonded to a nonmetal, and covalent, which is nonmetal bonded to nonmetal. And in this discussion, we're going to deal with the rule of thumb, if you will. Be aware that there are exceptions to this straightforward approach to, well, what kind of bond is it? You may have some compounds with metals in them that bond more covalently, and ultimately it's the properties of the substance that indicates how the bonding is occurring. So in this discussion we're going to look at what is the difference in the bonds, and then we're going to look a little bit at how does this affect the properties of the substances. Okay, electronegativity, we've discussed that in the previous unit. It's a measure of when an atom is in a bond, how strongly does it attract electrons to itself. And so this just is one way of showing that electronegativity increases up and to the right, with fluorine having the highest electronegativity. So let's look at what this means. Well, suppose we have 2 atoms that have equal electronegativities. What would you expect to see? Well, you would expect to see a nice equal sharing of the electrons. We would expect that the highest electron density in the bond would be halfway between the 2 atoms. Okay, equal sharing. If one of them is slightly more electronegative than the other, higher electronegativity, then you would expect the electrons to spend more time around the atom with the highest electronegativity. So we have possibly still sharing, but not an equal sharing. And then if we have a very large difference in electronegativity, what can happen is a complete transfer of electrons. One of the atoms has a very low electronegativity, and so when it bonds with the other one, completely gives up the electrons, and you have two ions formed, and then those oppositely charged ions are going to attract each other, and that forms the bond. So we have kind of a dual thing here. We either are sharing electrons and forming a bond that way, or we have a transfer of electrons which forms ions, and then those oppositely charged ions are attracted to each other, and that forms the bond. So let's look first at metallic bonding. When you were studying ionization energy, you should have observed that metals have low ionization energies. Doesn't take much energy for them to give up their valence electrons. And so in a metallic bond, they do indeed form cations, but the unique thing about metallic bonds are that these electrons are not being transferred to something else. They pretty much become free electrons. We sometimes refer to this as as C electrons, and so we have these free moving electrons moving around throughout the substance between these positively charged cations, and that's what holds it together. And again, this particular type of bond, as we'll see, is responsible for the properties we observe in metals. So here's kind of a visual of what we're talking about. All right, and let's look at this animation here. Okay, so we have the sea of electrons. They're delocalized. They don't really belong to one atom or the other. They're just moving around in between these positively charged metal ions. Okay, ionic bonding. Here we have between metals and nonmetals. And if you look for electronegativity, typically, the farther apart they are on the periodic table, the greater the difference in electronegativity. So you would expect metals and nonmetals to have large differences in electronegativity. And in that case, like we talked about before, we're going to have a transfer of electrons. So the metals tend to give up their electrons. The nonmetals tend to accept the electrons. And so we have the formation of positive metal ions, negative nonmetal ions, and those electrostatic attractions create the bond. Positive and negative attraction creates the bond. So here we have sodium and chlorine. And so you'll see sodium gives up its one electron, its one valence electron. The chlorine accepts it, okay? And note that each of them, by either giving up an electron or accepting it, then have a nice noble gas configuration. All right, covalent bonding. In this type of bonding, electrons are not transferred to make a bond, they are shared. Okay, and we've got two ways that they can share them, just like what we talked about before. But let's look here. We've got two atoms, and you see how once they share the electrons, now both of them again have 8 electrons, a full valence shell. Okay, so that's what they're bonding for here.